So hello friends, today we are going to start a topic that is very important in physiology, that is cardiac output. So we are going to measure cardiac output. So there are different parameters that we are going to study here. So first of all, let us study cardiac output. Before knowing what it is, I would like to tell you something about echocardiography. Echocardiography. Here what we do, that we have a signal transmitter. It is going to transmit ultrasonic waves. Okay, so here is my thorax. Suppose here is my thorax, here is my heart. What it is going to do, it is going to transmit ultrasound and it is going to be reflected from here, and it also acts as a receiver for this ultrasound transmission. Okay, so this is basically echocardiography. Why did I teach this? Because this is important. So before proceeding further to cardiac output, I would like to move to a topic called the methods of measurement. Okay, so just a second. Methods of measurement. All right. Here we can use different techniques like echocardiography. Echocardiography gives you information of various stuffs like the condition of heart valves. But when it is combined with Doppler, it can give us various other important things like velocity. Doppler, if you remember in physics, Doppler technique can be used to determine velocity when there is a change in frequency. We can detect the change in frequency. From that we can detect velocity, and from velocity of a fluid we can easily determine its volume. The volume of fluid flowing per second. Okay, so Doppler, we can determine cardiac output through echocardiography plus Doppler. Right? So this is the technique. Some other technique that can be used are fixed principle, and indicator dilution method. Is this good? I think we are clear with echocardiography plus Doppler. We are going to study these two things in detail. Okay, so let's proceed. First, I would like to show you indicator dilution method. Okay, so indicator dilution method. What this states is F equal E upon integral 0 to alpha C dt. Okay, where F is the flow, or basically cardiac output. Alright. E is the amount of dye injected, and C is instantaneous concentration of indicator in arterial blood. instantaneous concentration of indicator in the arterial blood. Alright, so if you're doing integral c dt, we know one formula, right? That suppose we are having an amount, anything called x, alright? Anything called x. So x is a parameter that changes with time, right? So if we want to find average of x, the average quantity of x, we indicate average by this symbol. I hope you know this much. So average of x, we know it is integral x dt over integral dt. Alright, so this term here, it is same as times integral dt, which is nothing but the time difference. Alright, so we can write this equation as F equal E upon average value of concentration into time. Alright, so suppose, for example, now let me show you an example. Okay, so if any question comes, you can use both this formula as well and this formula in your theory, but since you are in a medical school and not in a physics class, then most of the time you will be using this formula only. So let me give you an example. Suppose there is a person A, have injected 5 milligram of a dye in his arterial blood. Okay, so after 39 seconds, the average concentration of dye in arterial blood is how much? 1.6 milligram per liter. Okay, so what will be his cardiac output? So now how will we be proceeding? Cardiac output is nothing but flow, right? In 39 seconds, how much blood has flown through that particular portion? Suppose this is hand and I have injected the dye in his hand. Okay, so after 39 seconds, how much blood has flown? So indirectly we are measuring cardiac output through this only. So flow equals E upon C T. Okay, so it is 5 milligram divided by 1.6 milligram per liter into 39 seconds. Milligram gets cancelled. Okay, and this liter goes up here and it comes out to be 33.1 liter. Okay, so after this we can see that in 39 seconds flow equals 3.1 liter. So after 1 second, flow will be equal to how much? Right, and in 1 minute, what will be the value of flow? It will be equal to into 60, right? 60 seconds. So which gives our cardiac output to be equal to 4.7 second. I hope indicator dilution method is clear with you all, right? Next, what we are going to study is Fick's principle. Fick's principle. In Fick's principle, what we are going to study is that suppose this is my hand. Pardon my drawing. Okay. So here is my hand. This is my arterial blood. Okay. And this is my venous blood. Okay. And this is the capillary network in between. Okay. So what Fick's principles say is that oxygen O2 that will be consumed by hand, this will be equal to the blood flowing, that is flow rate, that we say flow rate, into the difference between arterial oxygen level and venous oxygen level. Okay, so this is the total amount of O2 that has been consumed by the entire hand. Here, this portion, the blood that has been flowing in this area, multiplied by the O2 difference between these 2 points. I hope you get this. Okay, so similarly, when we consider this with, suppose this is my body, okay, and I have my heart over here, and this is my aorta, and this is my inferior vena cava. Alright, I'm considering this a O2 and this as VO2. Okay, the oxygen concentration here and here. So the O2 consumed by the body is same as O2 that has been absorbed by the lung. Is this clear? The O2 consumed by the body is the same as the O2 that has been absorbed by the lung, and we can easily calculate it. Okay, so from this formula, O2 consumed equals flow into AO2 minus VO2. We can derive F equals O2 consumed divided by AO2 minus VO2, right? Yeah, so this is basically the formula. Okay, this is the formula that we are using here. If the same thing in the heart, we are using this formula. If suppose you have to use it for lungs, then it gets reversed, because pulmonary venous O2 is definitely greater than pulmonary arterial O2. Okay, so it is pulmonary venous O2 minus pulmonary arterial O2. Okay, I hope it is clear with you all. So flow in normal conditions, O2 consumed is 250 ml per minute. Okay, divided by arterial O2 in the aorta, it is around 190 ml per liter. 100 ml blood contains approximately 20 ml of O2. You know this, right? So it is approximately 190 only in 1 liter. So it is like that only. Yeah. So arterial O2 level is 190 ml per liter minus venous is 140 ml per liter. If we subtract, we are getting 250 divided by 50 equals 5 liter per minute. So this is the way fixed principle works. I hope you get it. There are a few other principles as well, like thermodilution method. Dilution method, in which a cold solution is inserted in the blood, but that method is a bit cumbersome and the questions are generally not asked. But if it is being asked, it is the same way you have solved this indicator dilution method, the same way you can solve the thermodilution method as well. Okay, so a few things are asked, that why is thermodilution method better than indicator dilution method, right? So the thing is that in the thermodilution method, you are just inserting saline, cold saline. Okay, saline is basically harmless for our body, while here dye is added, and the dye is also harmless, but it is something that has been added exogenously, that is not present in our body as such. So this is a major advantage, and the the cold dissipated to the tissue through the recirculation is not a problem, and it is easy to make repeated determinations. We can do repeated determinations through this technique. Okay, like there is circulation once, twice, thrice. We can do determination using thermodilution method, which is not possible through indicator dilution method. I hope you get this, and with this we come to an end of our first lecture, that is the methods of measurement of cardiac output. Thank you.